All right, it looks like it has slowed down a little bit in terms of new attendees to the webinar this afternoon, but just want to thank you all again for joining us and happy holidays. Welcome to the NARUC webinar series entitled Resilience for Regulators. Today's session will focus on the future of climate modeling for utility system planning and key lessons for state utility regulators. My name is Tremaine Phillips, Commissioner with the Michigan Public Service Commission. If you see a slight glimmer in my eye, that's not only because it is the holidays, but also because the Lions won another game this weekend. So that is a Christmas miracle to some of us. But I am honored to assist in moderating this afternoon's discussion. This discussion will feature two experts to talk about the impact and the improvements in regional and local climate data modeling. Our first presenter will be Dr. Ryan Berg, a Principal Business Analyst at Comet. And then we also will have Dr. Tom Wall, Program Lead for Engineering and Applied Resilience at the Argonne National Laboratory. So just a little bit of background on the flow of the discussion today. We will start off with just brief presentations from both Dr. Berg and Dr. Wall detailing Argonne National Laboratory's climate data research and their engagement with ComEd. And then we will open things up for questions from the audience. Certainly, I have a number of prompting questions here, but I please ask you all to not hesitate to put into the chat feature any questions or even comments that you may have during and following our introductory presentation this morning. But I will go ahead and not belabor things too much, pass things over to Dr. Wall and Dr. Berg to go into our introductory presentation. And please, if there is anything in addition to your background or your current work in this area, feel free to expound upon that. We'd be happy to hear anything else in terms of introductory remarks either of you may have. But with that, I will go ahead and pass things along, and then we can go into a Q&A session.
Thanks, Commissioner Phillips. And I think actually Dr. Wall is going to start us out. So Tom, let me hand over to you.
Cool. Can you guys hear me okay? I had to switch to phone for audio because my computer microphone was giving me problems.
Yep. We can hear you fine. Thank you.
Excellent. All right. Technology saves the day. Well, wonderful. My name is Tom Wall. As Commissioner Phillips said, I'm a program lead in engineering applied resilience at Argonne. I'm in our Center for Climate Resilience and Decision Science, which we established within the last year to really, I think, serve as a formal venue for collaboration across the lab for applying climate science and modeling to infrastructure and resilience problems. So what I'm going to talk about is a little bit about our approach to producing climate data and information, in particular for use by utilities and other infrastructure owners and operators. And then I'll talk a little bit about some work that we did specifically for ComEd to look at impacts to their grid here in Northern Illinois. And I think Ryan will then take over from there to really talk about how that's consequential for ComEd's business and the future of their grid. Next slide, please. So as I mentioned, we established the center a little over a year ago at Argonne. We have a pretty diverse set of expertise at the National Laboratory, and this allows us to formally collaborate on these types of projects. So we have an active group of climate scientists and climate modelers at Argonne, and I'll talk a little bit about the data that they produce, but it's a really unique resource. And so in order to apply that to, I mean, it's a great scientific resource, but I'm sort of more interested in the applied science aspect of that and how can we take all this cutting edge climate science and do something with it to inform decision-making or business cases. And so we established a center to combine that expertise with engineering, infrastructure analysis, decision science, large-scale infrastructure modeling to really inform at a very tactical level how we can plan or operate systems differently, given the looming specter of greater impacts from climate in the future. Next slide, please. So I'm going to step back and just talk a little bit about what climate science and climate modeling is. I think it's good context for what we do here at Argonne and how it's a little bit different, but unique and able to more directly inform infrastructure. So if you think of a climate, the sort of climate science 101, really, climate modeling is a process that just builds a gigantic mathematical model that models all of the Earth's climatological, oceanic, and atmospheric systems. And so you can think of it as the figure here shows as really a checkerboard that's laid across the globe. And within each of those grid cells, there's a series of equations that model all of the, dozens and dozens, if not more, processes that determine weather and climate. And so that's what that inset box is showing, things like evaporative processes, solar radiation, transfer of moisture from oceanic systems to atmospheric systems, and back and forth as precipitation. And this grid is not just a two-dimensional checkerboard, as again the figure in the top right shows. It's a three-dimensional system. In a global climate model that's trying to capture all of the global climate system, these grid cells are about 100 to 125 kilometers by 100 and 125 kilometers. So 100 kilometer by 100 kilometer grid cell is pretty big and doesn't give a lot of local detail, but it does a good job of capturing sort of, planetary scale or global scale climate dynamics. But if you're generalizing all of Florida as 3 grid cells, it doesn't give useful information to someone in Fort Lauderdale versus Fort Myers, right? The model would say the same thing happens in both places, which we know is not true. So if you go to the next slide, please, one of our processes here is then taking global climate data and what's called dynamically downscaling it. And downscaling is really just a family of methods to improve what we call the spatial resolution of a climate model. And the resolution is determined by the size of those grid cells. And the analogy I use is just like the pixels on the screen of your cell phone or a digital camera. If you have a greater number of smaller pixels, you get a clearer picture. And it's the same thing with climate models. So what we drive towards is, instead of having a 100 kilometer by 100 kilometer grid cell resolution in a global climate model, if we model North America, we have, in our case, we have a 12 kilometer by 12 kilometer grid cell. And so this is what's called regional climate modeling, and it takes information from the global climate models, and by effectively running it through a regional climate model is a process called dynamical downscaling. And so we're still modeling all the same physical processes and some additional ones because we have greater information about what happens locally. So we're still modeling all the physics of climate dynamics, but instead of modeling the entire globe, we're modeling just North America. And we are able to do this at 12 kilometer by 12 kilometer because, as the inset shows, at a national lab we have supercomputers. So that allows us to do this fairly efficiently because it's just a massive, massive computational exercise to compute future climate. We run the model a bunch of different ways. I won't get into too many of those details, but we look at a couple of different future emission scenarios. These are ideas of how humanity will either curb carbon emissions or continue to emit carbon in the future. So we don't really know what humanity is going to do. So this gives us a couple of different future scenarios. We take information not just from one global climate model, but from 3 different global climate models, and use that our regional climate model to really sort of translate those different ones. So by running a bunch of different ways, we have different permutations of the future, and we can begin to define the uncertainty space. So modeling always has uncertainty in it, but if we run it a bunch of different ways, we can begin to quantify that uncertainty and better understand what we think the range of plausible climate futures will look like. Next slide, please. So this shows what a 12-kilometer grid cell looks like. This is overlaid with the city of Chicago in that cross-hatched area, and each of those grid cells is a 12-kilometer by 12-kilometer grid cell. So we're really getting down to the metropolitan or sub-metropolitan scale. If you can advance one more slide, this is sort of our newest family of models that we're just currently running right now. We're advancing beyond a 12-kilometer resolution model to a 4-kilometer model. So each of these 12-kilometer grid cells gets broken up into 9 smaller grid cells. And, this gets down to, at a neighborhood level scale. So Ryan and I live in the same neighborhood here in Chicago, which is about 2 kilometers by 4 kilometers. So it really is getting down to, the size of our neighborhood and what future climate will look like here versus, say, further out in the suburbs where Argonne National Laboratory is located. Next slide, please. So we take all of this information, it produces a lot of data, and historically it's just lived on servers at Argonne, which we recognize is great for us and then the scientific community, but really we need to get this information in the hands of decision makers. So this is something we established and launched about 3 weeks ago. And so I think we won't get into a full demo of this now, but if you want to take note of the URL at the bottom of the page, we created a climate portal called the Climate Risk and Resilience Portal, or CLIMR. And CLIMR takes all of the climate data that we've produced from our regional climate model and puts that online for anybody to access. It's free. You can, it's a little limited in the types of climate impacts. It's mostly focused on temperature, precipitation, and wind at this point, but it's a very much a living breathing tool in further development. So we're gonna, we have a sort of phased approach over the next 12 months to incorporate additional climate data into it. When we finish the 4 kilometer model in about a year, we'll start putting that data on here. So again, we want everybody in the country really to have access to really high resolution, scientifically transparent, well vetted, peer-reviewed science, projecting future climate across the country, so we can all begin to better prepare for a more climate resilient future. So I've tried to tap dance a little bit on this slide long enough so you can write down that URL at the bottom, but I'd invite everybody to go visit that link. And there is a contact us link there. So if you have feedback on, hey, it'd be great if we had this other climate data, or gosh, I really don't like the color scheme that you have here, anything, we'll gladly take that, because we very much want to improve this and make it as useful to a broad community of users as possible. Next slide, please. So now I want to shift focus to what we've done for Northern Illinois, and this is our partnership with Comet. We started working with Comet in early of 2022, taking all the climate science and modeling that I very briefly ran through in the previous slides, and focus on modeling future climate impacts to Comet service territory in Northern Illinois, which is what the figure on the right shows. We worked, so Ryan was our main point of contact at Comet. He talked with, was interacting with a ton of subject matter experts within the Comet organization. We decided to focus on mid-century impacts. We can also look at end of century with how we run our climate models, but from a capital planning and investment perspective, it just made more sense to focus on nearer term impacts, sort of within the useful design life of infrastructure that would be either exist out in the field today or would be installed in the near future. We also focused on a highest emission scenario, and this is a very deliberate choice. What RCP 8.5 posits is really business as usual. If we continue to emit carbon globally the way that we have been for the last 10 or 20 years. And so it really forms what is the worst case scenario, and is, I think, from a risk perspective, is the most risk averse to plan around RCP 8.5. We all hope that we'll do better than that. But I think from a planning perspective today, Comet and most of the other infrastructure owners and operators that we've worked with are focused on planning around RCP 8.5. It's potentially overinvested in the system a little bit, but that certainly beats introducing some major safety concerns by planning for a lower emission scenario that we might shoot right past. Everything that we did was in comparison with a historical baseline, which was 95 to 04, and that's within Comet's 30-year look-back period that they use for planning purposes today. And I won't bury the lead here anymore, but the Northern Illinois climate that we projected shows it to be substantially warmer, more humid, and some changes in wind that we'll talk about. Generally the same, but there's some seasonal differences. Our focus for this study was really temperature, humidity, and wind. And this was part of a phased approach. So phase 2 of the study, which will launch hopefully early in the new year, will focus on precipitation and flooding and some other consequences as well. But there's a lot to learn about temperature in particular, as well as humidity and wind. So I think a phased approach was wise. Next slide, please. So this is one overview of temperature in northern Illinois, and this is showing changes to seasonal temperatures. So the top row is the seasonal average temperature. That is an average of daytime and nighttime temperatures. So if it doesn't look, it's looking at both changes in both daytime and nighttime. The middle row is maximum temperatures. That's typically a daytime high. And the bottom row is minimum temperatures, which is typically your overnight low. I guess what I want to point out with this figure is that the darker colors mean a greater change as compared with a historical baseline period. And what we see is that there's a positive change in temperature across all seasons, across the average, the maximum, and the minimum temperatures. But the greatest change will occur in winter, and in particular, those winter low temperatures. And this, as Ryan can talk about, this has implications for load forecasting, for heating versus cooling loads. And it's a lot less of a change than summer, right? So everything's getting hotter. Let me not, sort of ignore that fact, but winter is getting warmer to a greater extent than summer will get warmer across all temperatures. And we see this is, between 0.5 degree Celsius and 3.5 Celsius. So that's basically between 1 degree and 6 degrees Fahrenheit, between our sort of smallest changes in the summer and the greatest changes in the winter. Next slide, please. So in addition to, that was basically dry heat, but we also can, with the climate model, look at changes in humidity, which we reflected here as a heat index, which is effectively, that felt temperature in the shade, right? So it doesn't incorporate solar radiation and those other things. So it'd be sort of that shady, hottest temperature in the, that's affected by additional humidity. So what this figure shows is the differences in seasonal heat index values. And again, darker colors are greater amount of change. And this is not surprising, right? So it's the summertime maximum temperatures where we see the greatest additional felt temperature as a result of heat index. And really the minimums are of a negligible change. And it's really is that summertime high that will be, increased by up to 2.5 degrees Celsius. So that's about 4.5 degrees Fahrenheit of additional felt temperature as a result of heat index. And again, this has huge implications for, in particular, future load as a result of increased air conditioning demand, but it also has some implications for, additional moisture in the air can affect equipment and other things. Next slide, please. So this was an interesting figure that we spent a lot of time talking to Comet about. And what this effectively shows is the change in exceedance. So the percent of days per year, the amount of time per year spent above a certain temperature or days that exceed that temperature. And so if you look at that x-axis, it's 0 to 100. So that's, 100% of the days in a year above a certain temperature. The y-axis is that daily average temperature. And daily average temperature, again, this factors in daytime highs and nighttime lows. So it's an average of both of those. You think, gosh, well, we have hotter days in Chicago than some what's shown in this figure, but it is that daytime nighttime average. We spent a lot of time really particularly focusing on the left-hand side of this figure. The red line shows the base period, and the blue line shows what's projected at mid-century. And you see about a 2 to 4 degree increase in temperatures sort of across the board. And so if you look at that red line, where it shows 20 on the x-axis, what that's saying is that about 20% of the year will have an average temperature above about 1 degrees Celsius. And so if we focus on the left hand, side of the figure, what that's really showing are the daytime maximum temperatures. And what we see is that in the baseline period, in that red line all the way at the left, we have about 2 days per year that exceed 30 degrees Celsius or 86 Fahrenheit. And remember, that's an average of the daytime high and the nighttime low. So the daytime high would be above 86 and the nighttime low would be below 86. There's about 1 day per decade that's above 35 degrees Celsius average, or 95 Fahrenheit. Again, it's hotter during the day, cooler during the night, so it averages out to 95. By mid-century, the 30 degrees Celsius, increases by about 3 days per year, so not a ton, but the 95 degrees Fahrenheit average daily temperature has a fourfold increase of about 4 days per decade, which doesn't sound like a lot, but has major implications for equipment design, design life, derating of transformers, things like that I can let Ryan talk a lot more about. This is sort of a first stab at this in this study. So we're really, in phase 2 of the project, going to focus a lot more on temperature extremes and see if we can get even more detail about what's happening at the, both the far left and the far right-hand side of this figure. Next slide, please. So a lot of that, the last figure was, based upon a lot of discussions with subject matter experts, and they started giving feedback in response to some of the earliest figures that I showed, saying, yeah, these averages are great, but can you help tailor this a little bit more to a specific utility case? And that's what that previous figure was. Another one that we focused on was changes in heating degree days and cooling degree days, which is a metric used for, again, load forecasting. So it's sort of looking at the divergence from 65 degree Fahrenheit, quote unquote, comfortable temperature. And so days below that are heating degree days where we need, additional space heating to be comfortable. What we show here is that there's an increase in, a decrease in the heating degree days, right? Because everything's getting warmer, so we don't have to heat as much. And the greatest decrease is in winter. So if you look at that, the shading is a little bit different on each of them. So maybe in that third bullet down there, that first sub-bullet shows that winter decreases from 341 to 476 fewer heating degree days. If you go to the next slide, this shows cooling degree days. And cooling degree days, we see an increase, again, because everything's getting warmer, but not to the same extent, right? So that summer increase is between a half and a quarter of what the change in heating degree days is. Cooling degree days increased by 173 to 287. So again, this is consistent with the general projection that I showed a couple slides ago, that everything is getting warmer, but winters are getting warmer to a greater extent than the summers are getting warmer. And again, this has implications for load forecasting across the region. Next slide, please. So the last thing that we focused on in this study, and again, the study is public. We can put a link in, in the chat where you can download the study. There's a lot more figures, a lot more detail for everything that I've presented so far. The last impact that we looked at was wind and changes in wind. We can't get to extremes like would occur with a derecho or a major storm, but what we can really look at are changes in general wind characteristics, which really might be more applicable to looking at wind generation and the viability of that, as opposed to damage to structures or lateral loading from extreme winds. Generally speaking, across northern Illinois, the average annual wind speed doesn't really change much, right? A half a percent change is really within the normal annual or interannual variability that you see year to year. What's really was striking to us is that winter, summer, and fall all show a decrease in wind speeds, but spring gets windier. So again, in particular, spring gets windier in the southern portion of the region. And some of the greatest decreases in wind speed is that fall in the northern and southern portions of the region. So again, sort of interesting information for ComEd and for the region in thinking about, for example, changes to renewable energy, but also could have some implications for, just general windiness, which can help cool conductors, can cool equipment. If wind is going down, particularly in summertime, when it's hottest, that may have implications for equipment cooling, for example. Next slide, please. So this is the very last thing that we looked at that was not necessarily a specific climate impact, but really was a request from ComEd that said, hey, certainly there's other portions of the country that experience today the climate that we will experience in the future. Can you help us identify where those locations are so we could begin a dialogue with utilities in those regions to better understand what they're doing to cope with these types of climate impacts, and we could learn some best practices. And so we call this a regional climate analog comparison. And really what we see is the yellow bands are the areas that have the closest one-to-one comparison of what they're experiencing today as compared to what Comet will experience at the mid-century. And then the red and the blue is, I think, 1 or 2 standard deviations away from that. But focus on that yellow. And what we see in the upper left for the minimum temperatures, for example, Southern Illinois' minimum temperatures today is what the Chicagoland area and Northern Illinois may experience at mid-century. Average temperatures and maximum temperatures are more akin to what the middle part of Illinois, so Springfield, Champaign-Urbana. I thought the heat index was particularly interesting. Most of central Missouri, what they experience today for heat index is what Northern Illinois will experience at mid-century in the future. So again, this gives ComEd some indication of what other parts of the country might be experiencing today, what we'll see in the future. And certainly ComEd's part of Exelon, so they have utilities in other parts of the country. Maybe even within the same organization, there's an opportunity for some information sharing to benefit future climate resilience planning. Next slide, please. So this is the end of my portion of the presentation. If you have questions, the email up there goes to our general center inbox, but I monitor that, and I'm happy to handle questions that way. I guess, Commissioner Phillips, maybe I'll hand it to Ryan, and he can address some of his content, and then we could handle questions in the Q&A afterwards.
Yes, I think that would be great. And again, thank you for the very detailed presentation. I want to figure out how to use the phrase dynamically downscaling in my normal verbiage, but I do appreciate the summary there. And then also watching today to go ahead either through the Q&A function or the chat function, put forth your questions, and we'll make sure to ask them this afternoon. Ryan, it's on to you.
Sure. Thanks, Tom. Thanks, Commissioner Phillips. We have at ComEd, we've been looking sort of carefully and trying to think through with Argonne what these implications will be for us, and particularly from an engineering perspective. And what I'd like to talk a little bit about today is how we see that as increasingly informing some of the day-to-day work that engineering teams do around grid and grid processes. And in order to see what that means for us, it's kind of important to recognize that today a lot of the engineering we do is backward looking. So we are constantly informed by a retrospective view of the operational capabilities of the power system. So we look at system peak, which is informed by the weather that has already occurred in the region, and that weather is then shaped by the HVAC equipment that people already own in the region. So when we start projecting into the future and changing those dynamics and looking at increases in temperature, we enter this unknown, right? This forward-looking view that has a new level of uncertainty. And we've been looking to Argonne, and as in this partnership, to help inform us about what that future might look like. And they have provided us with a lot of information, sort of in waves. Initially, we came to them with an understanding of what some of the system sensitivities might be. So on the engineering organization, we got together a group of subject matter experts that ended up being 50 or more people from across our teams who, in reviewing some of what Argonne could do for us, came back with questions. So one of those was this comparison of what region are we most going to be like in the future. That was a question that came from an engineering team. Wouldn't it be great if we could know how transformers are being designed in a region today that will experience that is experiencing the kind of weather that we'll experience in the future? That would help us to know something about these changes. the backward-looking view, it gets us a long way, right? I mean, if you think about system reliability, we look at the performance of different assets and try and understand where that performance can be improved upon. And so we are constantly relying upon our kind of real experience with equipment in the field in order to inform our engineering practices. But I think our engineering teams found that they had to go back to the drawing board and sort of start asking these kind of fundamental questions of what, how would transformers be rated, not according to our experience in the way we operate them today, but how would they be rated under these different operating conditions? So those teams then came back with some IEEE standards and threshold temperature thresholds that were used in equipment ratings, and so 35 degrees Celsius average temperature is an example of one of those thresholds, where in the IEEE standard for power transformers, above, but they kind of normalize to an average temperature of 35 C. So if we start seeing greater than that, that it has implications for each of those days for the degradation of this equipment. And for those of you who don't have a background in power systems engineering, I don't. There's quite a learning curve around what some of these implications can be. I think the key thing to understand about a lot of power systems equipment is that it is sensitive to the ambient temperatures that in which the equipment is operating. So you get two different aspects of impact. One aspect of impact on temperature comes from additional system load, where more people are running air conditioner, their air conditioners are cycling more of the time. So that causes an increase in the load that the equipment has to handle. And then in addition to that, the equipment has less time to cool. And as the equipment is unable to cool, the temperature of the oil in a transformer or the temperature of a conductor might increase to a point where you start having a degradation in the insulation. And that thermal degradation is the most significant variable in the durable life, the asset life of that equipment. So the more hours that you operate above a certain temperature, where the top oil temperature on a transformer is higher than a certain threshold, the less life you will get out of that asset. So the concern here is that if we start seeing conditions that we've never seen before, and we're not ready for those conditions and not planning around them in the way we set standards and the way we operate the system, that we might operate equipment in a way that really causes additional cost to the operation of that equipment and ends up putting a burden on our communities. So we want to manage that proactively, and we want to do so by setting standards and thinking critically about like how we would design our equipment and configure our circuits. And then we also want to do that kind of in concert with our communities. We want to look at these impacts not only from a asset kind of focus, but also by thinking about what additional risks are going to be imposed on our customers that we need to be ready for and help to manage in a kind of crisis management perspective. So I think I'd like to kind of leave some room for discussion here. We had a lot of really helpful content from Tom, and I want to make sure everybody has time to engage with him. But overall, a key takeaway from our experience doing this is how region-specific and detailed this analysis can become. I mean, we've gotten literally into the weeds on thinking about vegetation management and what happens to different tree species as the growing season lengthens. Will we expect to see additional generations of pests that impact our polls and our poll inspection cycles? Will we see additional growth on tree species that would cause us to change the cycle of vegetation management that we have in the region? These can have a pretty significant impact on our operational, basic operational environment, timeline, staffing, lots of other things. And so we want to make sure that we're thinking that through. That does not mean, and Tom has emphasized that this is like phase one of X. I mean, it's certainly two at this point. We are not at a point where we're ready to say here's our adaptation agenda, right? These are the 10 investments that we're going to make in the next 30 years for climate change. We're much more in a point of retooling some of our engineering processes and building some additional understanding on our teams in order to make sure that we're informing and updating our practices. So I think going forward, we still have a lot of questions lingering in the air, but we're I think benefiting a lot from the conversation.
Thank you for that, and thank you once again. This is really a fascinating topic, and thank you for detailing more about how you all are using this data to not only compare with other service territories or other utilities who are currently facing the same climate challenges you are now, but also those utilities that are facing the climate challenges now that you all will face in the future as your weather trends continue to change. That's something that I can already see us wanting to incorporate here in our jurisdiction in Michigan, and also encourage our utilities to do. But that requires really good, more regional, more local climate data in order to kind of do that comparison and analysis. So that's hopefully what we will have here, increasingly so from the Argonne National Laboratory. I do want to go back to you all and, like any good Marvel comic, talk about the origin story and how you all came together. Maybe you ran into each other at a coffee shop nearby, and that's how this whole project started. But I do have a question that just came in, which is, I think, one of the key questions that we have had here at the commission as well, and it's from Joseph Abraham. So thank you for this, but can you discuss the potential for error in downscaling larger scale model outputs? And is there a general difference in the source of error between statistical versus dynamic downscaling? So yeah, if you all could both comment on this as much as you would like to, that would be really helpful for all of us.
Tom, I think you're still on mute, but you are the right man to answer this question. So I'm happy to punt it to you.
Cool. Can you hear me now? Excellent. I was muted on my phone and on Zoom, so good. Thanks for looking at Ryan. What I was saying is, this is a great question, and there's a lot to unpack here, and we could certainly spend the rest of the call talking just about this topic. But so let me take sort of two things. The first is going from global scale climate modeling to local scale through dynamic downscaling. Sure, it's another model that takes inputs from a previous model, so it introduces some additional sources of uncertainty. But I think, again, that's why we try and run the model a bunch of different ways to, as best as we can, quantify that uncertainty. So, as I said, we take information from 3 different global climate models. We did that very deliberately, and we chose 3 different models because they each have model different climate dynamics. They have what we'll call different carbon sensitivity. So you increase the amount of carbon in the model, and one of them shows a little bit of an increase in temperature. The other global climate model shows a moderate increase in temperature, and the third one shows a greater increase in temperature. So we're trying to, by selecting 3 models, capture some of the uncertainty in a global climate model. And then we run our regional climate model with each of those separately. So we're seeing how that translates into local climate. And again, a lot of it is trying to quantify that uncertainty. Part of model validation involves a process called backcasting, which is where we're running the regional climate model for a historical period and then comparing the outcomes of the climate model with just record of what weather and climate looks like and seeing how well the model effectively recreates that. And so that's a way that we can, sort of tinker with and tweak the model to try and make it as accurate as possible at recreating historical information so that we have greater confidence that it's giving us useful information as we move into the future. The second part of your question was about different downscaling techniques. So there's broadly two families. There's dynamical downscaling, which involves some sort of a regional or additional climate model that's over a smaller spatial domain, right? And the question is, why don't we run a global climate model over a smaller spatial domain at higher resolution? That just comes down to computing resources. We just don't have, even today, computers fast enough to do that. So this approach is still very valuable. The other approach, as you alluded to, is statistical downscaling, which doesn't require a supercomputer. You can do that on your laptop. And what statistical downscaling does is it takes information. You're looking at a region and looking at what a global climate model said in very coarse resolution will occur over that region, and saying if the global climate model says X amount of inches of rain fell, then you can look historically at, well, how much flooding did that translate to locally at different points within that larger region, and create statistical relationships so that in the future, when the global climate model says Y amount of rainfall falls on the ground, you can calculate what the local flooding would be as a result of that, or what local precipitation would be. The challenge there is it introduces two additional problems, and the first is what we call stationarity, that we assume that the relationships that we've established historically will continue into the future with changing climate, but there's such complex dynamics that I think that stationarity assumption is pretty easy to challenge. And then the second one is really that you're limited to only the types of climate impacts that we have observational record for, right? So we don't have a long historical record where we've observed soil moisture, for example. So we can't statistically downscale soil moisture because we can't build those statistical relationships based upon historical data. What we can really do is we can do it for temperature, we can do it for rainfall, we might be able to do it for wind and a couple of other things. So it's limiting in the types of climate impacts that you can examine into the future. So that's not necessarily a challenge of accuracy or uncertainty in the model. It's just a limitation of data, really, and having an adequate historical record of different impacts.
And Tom, let me just add one gloss here. We've been learning a lot of vocabulary here. So if anyone is like Commissioner Phillips trying to get your whatever holiday meal vocabulary queued up to impress your family, there's plenty to pull from here. One of the things we're really excited about in dynamical downscaling is having a kind of weather model based approximation of what some of the impacts of the global climate mid-century can be. In particular, we're thinking about severe weather like thunderstorms. And that's something that the coarse 100-kilometer scale global models really don't have very much information about. Anything, those associations for weather conditions that we've never seen before, we don't have a lot there right now. And still at the level of downscaling that we have, the 12-kilometer model that we've been working from so far, we also don't really have it. So the industry is really egging Argonne on, trying to get some more information, because we'd really like to know if it turns out that what is for us a century storm is going to become a decade storm, and a decade storm is going to become an annual occurrence. That would really inform some decisions that we'd make about reliability and resiliency. And we'd rather make those decisions, with an eye to the future where you can get all that benefit rather than waiting until the storms come and and the consequences are already here. If you look at the adaptation studies that have been done in the industry, and high-profile ones, Southern California Edison published one this year. Con Edison has worked on a couple different phases of theirs. Those were really PUC ordered following severe events. So that's in the industry, a lot of adaptation is happening in that style of reactive, asking us to be more proactive. So I think that's really the next phase of this, is trying to get the models to push into the areas where we know that there's risk right now, and we want to make sure we manage that future risk.
Thank you both for further elaborating on those points. We do have another question here that I want to make sure that we get in before our time closes. This is from Anna Brown, and it looks to be directed towards you and me, Ryan. But looking at how are we potentially looking at quantifying avoided damages and factoring in that rationale into our investment strategies as we look at integrated resource planning processes or kind of long-term infrastructure investments. I know that Ryan, we both kind of have open IRP cases that either involved in or before us, but if there is anything that you could elaborate on here in this question, and certainly dance around any restrictions that you have with the process ongoing in Illinois, please feel free.
Sure. Yeah. I mean, it's a live question, and I think as we look to these climate models, the really high level thing to be aware of is that you get this climate data, and then you have to translate it through into some system impact, and that translation process is really, for us, the big first stage of it is understanding the asset level impacts. So there's a whole nother phase of that about as you get into the investment domain, and not only is that kind of open docket kind of thing for us, but it's not yet where we are. So I think in our process, where we are today is really just fully appreciating what these risks might be, and starting just in a very, very early age to look at some of the adaptation strategies that might be available to us in addressing them. So going forward, though, it's not only a problem of kind of quantifying the investment benefit, but it's also a problem of linking that into some other sources of uncertainty that we have on the system. So we have rising adoption of DER, we have increase in beneficial electrification, but we have some through the Inflation Reduction Act, future of heat pumps that are much more of a live issue today than we thought that they were going to be a year ago. And so all of these things are changing the planning dynamic, and we have to, in our work, we have to figure out how to account for all of them. So I think climate is a key missing variable, and one that there's a lot of interest in our industry to try and account for. But the whole calculus of where is the infrastructure risk and how do we manage it, it's really about putting those pieces together.
Thank you for that, Ryan. And Anna, in response to your question here in Michigan, no, we have not gone that far in terms of looking at the potential for quantifying avoided damages and incorporating that into our regulatory processes or into our utility filings. What we have done is that in response to Governor Gretchen Whitmer's 2020 executive directive, which created the Healthy Climate Plan, as well as established goals that would lead the state to economy-wide carbon neutrality by 2050, is that in our integrated resource planning process, we are requesting of our investor-owned utilities to put forth additional modeling scenarios that would accompany their filings And those modeling scenarios would be to align with those decarbonization goals that the governor has set out, the interim goals, as well as the ultimate goal of carbon neutrality by 2050. There's also been increased cooperation and coordination, particularly with our Department of Energy, Environment, and Great Lakes, to encourage them to be more involved in the intervening process for our integrated resource planning cases, and to encourage them to be more proactive in providing additional data and information on what they believe will be the potential impacts on the climate of those modeling scenarios, and just having them be a much more integrated part of our IRP case proceeding process. So that's at least where we've gone in terms of our first steps. But from seeing what ComEd and what others are doing, I think it provides us a good sightline for how much further we could go in this area. If I could ask Ryan and Tom, what was kind of the impetus here behind this collaboration? Was this something that was urged through the regulatory process, through the legislature, or was this just seen as a natural collaboration that built on other partnerships in the past? And then, Tom, if you could talk about what this collaboration, I guess, portends for other states, other utilities across the country. Certainly, you're encouraging all of us to visit and to utilize the data that's on the website, but are there going to be other studies like this replicated across the country?
Yeah, so let me just the ComEd piece of this. We have in our state a fairly forward-looking energy law, CEJA, the Climate and Equitable Jobs Act that passed in September of last year. And within our work to try and think about as a company what we need to do to be fully compliant with it, the climate is just so front and center for us as a not only an area where we're trying to support state goals in the mitigation of climate risk, but also something where we view adaptation as being kind of center in our public responsibilities. And so we put together a program with Argonne. We were following a script that had already been established. Gil Quinones, our CEO, came from NYPA. NYPA and Argonne had already started, and we slightly beat them in publishing, but they have been working really hard on a climate study, adaptation study as well. And so Gil had some familiarity with Argonne and their capabilities, and it was a natural fit for us given the shared geography and a lot of other shared relationships. We work together on a lot of future energy kinds of projects and thinking about EV impacts and other things too. So Argonne is a real resource in the region and a natural fit for this work.
Yeah, I think the second part of the question is sort of what's the future outlook for this? And a lot of the information that's on the Climate portal that I showed in my presentation is information that we learned about through our collaborations with NYPA, with New York Power Authority, and with Comet. And so I think we are continually getting better at producing utility relevant climate data through these types of collaborations. So I think that we're looking in 2023. We have a couple of additional partnerships for studies on the horizon. Until those are solidified, I don't want to get into too much more detail, but I think that there's still a lot of need for these more direct partnerships, because that helps us do better science that we can more directly connect to actionable outcomes. Our portal has, for example, we put heating degree day and cooling degree day information up there. That was a direct result of what we did with Comet and sort of their discussion of how useful that would be for load forecasting. And we thought, well, we've gotten through the process of calculating that for Northern Illinois. Let's just extend that to the entire country and put it on the portal. And so that type of partnership helps us drive better, more actionable science. So I think we're looking forward to supporting more of these studies and building a more robust online tool that then in particular, smaller utilities that don't have, as many resources to engage in this type of larger study can then benefit from that. So I think that it's, we're only going to all be resilient if all of us are resilient together. And I think that, it's great leadership from Comet and NYPA and Con Ed and SoCal Edison and the others who've done this so far to really lead the way, and a lot of others get to benefit from that. But I think that there's still a lot of good work to be done to more fully realize that.
Thank you for that. And I know we only have a handful of minutes left here. I don't see any other questions in the chat, but I'd like to thank you all. I know you pulled together a similar presentation during our NARUC meeting in New Orleans. Maybe you're going on a 30-city tour after this to continue this education and discussion. But before we leave here today, is there just anything that you would like to leave with us as regulators, as PUC staff, as employees of investor-owned utilities across the country? Any other points of note that you would like to leave with us? And were there any particular challenges on kind of getting this project started and working, particularly you, Ryan, working within your organization and kind of getting some momentum behind really digging in and utilizing some of this climate data that Argonne has brought forth?
Well, I can speak just for one, I think, big advantage that we've had. We have run this study really within our engineering organization. And so if you contrast that with some, say, public reporting for the purpose of investor information kind of exercises that different companies do, ours has been a ground up engineering study. And that's been a challenge and a huge advantage. I think Tom and team have been surprised at some of the detail that we were able to get to in 5-6 month process by virtue of having, from our senior vice president and CEO level on down, a lot of support for the engineering initiative here. We've had engagement from our customer ops and from other teams trying to think about community impact. So it's not that the engineers are the only ones who have to be worrying, but I think that when it comes to the system impact, a lot of that gets driven that way. And I did want to mention also, many of you are engaged with EPRI and hearing from them in different processes and a part of different things that EPRI does. And EPRI has stood up an initiative called Climate Ready, and it's promising to provide a lot of really detailed asset level studies of climate risk. And so that, we're participating in that. A lot of other utilities are. And I think that is going to be also, like Argonne, a real resource nationally as we start navigating these kinds of risks, and they're accelerating. So I think we know we have a lot of work left to do to be ready.
I'll just make one very final comment. These types of presentations, I usually end by saying that, I think we've admired the complexity of the problem of climate change for so long, thinking that the data just isn't there to support, climate action and greater resilience planning. And hopefully my presentation gave you some insight that, yes, we really can do that. But here I have the unique benefit of having Ryan here saying that, the proof's in the pudding, right? We really can do something with the information that we have today. So I think we can move beyond sort of admiring the complexity and the challenge of climate change and really proactively plan for resilience. And Comet's a great example of an organization's ability to do that with the science that we have at our disposal today.
Well, thank you very much once again, Tom and Ryan. Thank you to NARUC to pulling together or continuing to pull together this series of webinars around the topic of resilience. I do hope that you all take Tom's suggestion. Please go and visit the website to see what sounds like pretty freshly minted data and access there. And we look forward to seeing what other iterative developments you all make and what other additional data is provided in the years to come. I hope that you all have a great holiday. Please safe travels, and just once again, go Lions. Thank you this afternoon.
Thank you, Commissioner Phillips.